start up. Now it's time to get to the page. Okay, the one page that I think is going to be helpful. Used to be some prompts. Go to cisp310. All right, so with your homework assignment, this particular note here is going to be helpful. In topic 2, you want to read addressing modes and memory allocation. And in there, okay, so even there are several links. So let me go to the linked document here. So in here, you definitely want to read section 2, the move instruction itself, because you will have to know, which one is the source operand and which one is the destination operand, because not knowing which one is not going to help with your homework assignment. Operand categories is a general description of what type of operand we can use with just about any architecture. Immediate means the value is a part of the instruction itself. Register means the value is coming from a particular register. Memory means the value is coming from memory. It is the content at a location in memory. So those are the 3 types of operands in terms of categories. Section 4 talks about memory section, memory allocation, labels, and the current location, which is not particularly helpful, especially in the homework assignment, but it is a very useful concept that can come in handy sometimes. So memory sections talk about dot text versus dot data, and you can switch between those two by using what we call a directive. So dot data is called a directive. Dot text is also called a directive. A directive means it does not generate any runtime code. It is an instruction to the assembler in this case. Okay, it is an instruction to the translator and say, oh, from here on, translate into that book instead of the other book. Okay? But dot data does not really generate any actual code in the executable. So that's that we talked about already. So we go back. Memory allocation, we talked about several of these, or most of these we talked about already. Dot int is going to allocate basically chunks of 32-bit things. Each value is a 32-bit, and you can have as many as you want to. So the syntax of this basically says dot int has to be followed by a particular value. But if you want to specify even more values, you can use a comma separated list if you want to. Okay. This is a syntax, it's also a regular expression kind of syntax where the curly braces basically indicate the boundary of a group. So in this case, the group consists of a single comma and a token, which is the value. Asterisk means any number of the previous name. So in this case, it is any number of the previous name, and each previous name is a comma with a value. So basically, it's just a comma separated list of values. Dot word allocate 16-bit chunks. Dot byte allocates 8-bit chunks. Dot fill we have not used yet. Okay, so I'm not gonna talk about it at this point. But you need to read about this section because it really tells you how memory is laid out and initialized in your homework assignment. All right, moving to the next section, labels. Now labels are particularly important because in general, a label is nothing more than a symbolic name that will eventually be associated with an integer value of some sort, okay? So you can use this particular syntax here, like 3 equals, digit 3. Then just highlight which portion we are talking about here. So this is one way to define a label, but in this case, the label 3, THREE, is really just a symbolic name for whatever the value that we defined it to. In this case, it is the numerical value 3. Okay, so that's one way to define a label. But there are other ways to define labels too. So the other way to define a label is to define a label to represent the current location in each section. So in this case, the dot, the single period symbol represents the current point in memory allocation for a particular segment. So we can talk about the text section or the data section, but as you continue to write the program or continue to use .in, .byte, and .word, you will be consuming more and more more and more memory. The dot is basically just saying, okay, on this page that we are talking about right now, that's the current page. Dot is the current page, or the page number of the current page. Okay, so you can define labels using the dot, which is kind of like this. So we can say prompt equals to dot, which means that dot refers to the current location in either the data or the code section. In this case, I don't know which one because it's not indicated. But this dot is really the location of the uppercase E character in enter a value. So the definition of this label, which is prompt equals to dot, basically is just saying prompt becomes a label, and that label is the location of the first letter of enter a value. Okay? And so you can use this syntax if you want to. You can say label name equals dot to define a label for a particular location in your program. But it is much more common to use shorthand. The shorthand is to use a colon, which is what we have been using in this class, because prompt colon is basically the same thing, exactly the same thing as prompt equals dot, which is okay, the current location now has a name, has a label, or has a bookmark with the name of prompt. Now, the current location is a page number, and the number is an integer. So for the most part, in this case, prompt is really a number. It's really just an integer. You can perform addition, subtraction, multiplication. You can do anything you can normally do with an integer with prompt in this case. Are we still doing okay so far with the concepts that you need to understand for your homework assignment? Sort of? Okay. So this part then we move on and talk about the actual specific addressing modes for the i386 architecture. So almost everything before this is kind of in general is applicable to just about any architecture, and almost every assembler has similar features, if not exactly the same thing. This part talks about specific things to the i386 architecture, and I mentioned that only 5.1, 5.2, and 5.5 are needed for the time being. I'm changing the order of how the concepts are introduced. 5.1 is just immediate operand, which means as a part of the instruction, there is a value specified already, and that value is the value of the operand. 5.2 means instead of having the value as a part of the instruction only specifies, oh, take a look at that particular register. The value of that register is the value of the operand. 5.5 is saying, instead of looking at the value as instead of looking at the register to get the value of the operand, use the register as an address. Go to that particular location in memory, grab the content at the location, that becomes the value of the operand. And those are the three different types of addressing modes that we have talked about, and you only need to understand those three for your homework assignment. Are there any questions about these concepts and how they relate to your homework assignment? There's also one piece that we talked about, not in the previous lecture, but a few lectures back. And that one has to do with how a register is chopped up into smaller pieces. And I believe it is discussed here. Okay, so 5.2 talks about the register operand. Do you guys still remember I used a spreadsheet to demonstrate how EAX, for instance, is a 32-bit register, but you can refer to the least significant 16-bit using the name of AX, or bit 0 to bit 7 as AL, and then bit 8 to bit 15 as AH. So those are names to refer to different parts of the same EAX, the same 32-bit register. Okay, and you need to understand that part as well in order to do your homework assignment. So are there any particular question related to what I've just mentioned? Nope. All right. All right, so if there are no questions, I really don't know what to say about all of these topics because I think that covered it all. Plus, the previous lecture is particularly helpful because it talks about how to use the X command and also the print command in GDB, and that is really helpful because you can use X to dump memory content. So you can actually visualize and say, oh, okay, I can see that .int become this particular .int, gives me this content in memory, and then you can ask, okay, but how do I get there? Okay, because I need to copy this byte over here in this register, so I know the location where I want it. But with the instruction that you are given, you have a lot of restrictions of how you can do it, which is good. A lot of restrictions mean you can only do it in like 1 or 2 ways, instead of there are 20 gazillion ways to do the same thing. Any questions? I mean, you guys are awfully quiet today.
Would info register work as well?
Info register will also display the value of a register. So info register EAX is the same thing as print $EAX. So they do exactly the same thing, just 2 different ways of doing it.
And if you leave off the specifying the register, it will print them all?
Yes. If you just say info register, or in short, I space R, and then press the enter key, it will display the content of all the registers. So if you want to display multiple registers to begin with, that might be a time saver, but it's not functionally any more or less than just print. Any other questions related to your homework assignment? No questions? Well, I mean, if there are no questions, we're going to move on and talk about the add instruction. And so I got to make sure that you guys are really good with everything that we have talked about so far. Are we good? Okay. It's hard to say, it's hard to determine whether you guys are okay, ready to move on or not. Because if you have questions, this would be a good time to ask questions like, yep.
I don't know if this is the place for it, but just the actual going through the program, seeing how it moves and stuff. I got the homework right, but I'm not solid on when you do this. It moves an address here, and then it moves.
Okay, we can take a look at the homework assignment, and okay, so we can do this. So what we can do is I can take a look at the homework assignment, which is really just a file that is already given to you, and you have to change just 3 question marks to do what the assignment asks you to do. So the question is, how do we do that? So I can kind of give you a general approach of how to do it, and basically how to look at it.
And that's what I'm asking, yeah, how to look at it.
RGZ. Okay, so here's the source code of the program. We have dot data, which means we're switching to the data section in order to allocate a few bytes and get those locations initialized. Dot byte, dot word, dot int, and then the L1 label is basically saying, okay, at this point, okay, the next byte that I'm allocating is going to be at location L1. That's what L1 is. It's just a page number. It's a symbolic name of a page number. And what .int L1 minus 6 means is take whatever L1 is, subtract 6 from it, and that becomes the value of what these 32-bit is representing. In other words, on a particular page of your notebook, you're writing down the page number of another page of the same notebook. That's basically what it is. Is that concept okay with you guys? can you on your notebook? Okay, you guys, most of you having a notebook right now. So imagine that you have a notebook that has page numbers. Okay, is it possible for you to write down the page number of the same page or another page on a particular page of your notebook? Yeah, right? So that's basically what .int L1 minus 6 and .int L1 minus 7 are doing. Okay, we are just writing down the page number of certain locations, or we're writing down the address of certain content as those 4 bytes. Those 4 bytes are integers, and they correspond to the location of something in memory. To approach this particular homework assignment, if you're trying to get started, you have to start with this. I mean, there's no way to get around this particular one. Is you have to start with, okay, what is EBX? What is the value in EBX after all of this is done? Okay, so you have to start with that. Once you start with that, then you can say, well, this value is specifically in base 10, and base 10 is not particularly helpful for a homework assignment like this. You need to first convert it into a way where it is easy to see the actual binary contents in zeros and ones in register EBX. There are several ways to do it. We can either go online, find something that can help you print a base 10 number in a different base, or you can use GDB, print / whatever format. Okay, you can use binary, you can use hexadecimal, you can use octal. Choose one that works well for this particular homework assignment. Okay, so once you can see the content of EBX in a convenient base, so they can chop it into individual bytes, then you can look into the last instruction and sort of work your way backwards. Okay, so the last instruction is this one. In other words, this is the last instruction to overwrite bit 0 to bit 7 of EBX. Okay, so you find out what that byte looks like, and then you go to the earlier portion of this program and say, do we have that byte somewhere in here? If you find that byte, then you say, okay, but how do I get to that byte? Well, the most immediate clue of how to get to that byte is the indirect operand here. In other words, you have to find out what EAX in parentheses is really saying. Okay, remember we only have 3 different types of operands. We have immediate, we have register, and we have indirect. Okay, so with every single operand in this particular program, you have to identify which one is which one. Okay, which one out of the 3 is this particular one, and so on. Once you identify what is this particular operand, then you go, okay, I can see that EAX in parentheses is this type of operand. So now the next question is, how do I get that operand to specify a value of this particular byte? Okay, and that's how you can work your way backwards to figure out what eventually has to go into the question mark. So I'm just kind of describing the general approach, how to get started, how to look at the program, what concepts are important, when you are dealing with this program. As for the specifics, like, what type of GDB command would I need to use, how to look into memory content and stuff like that, I have done that in the previous class already, so the YouTube recording of that particular class will be handy. All right, is that okay? All right, if that is okay, we're gonna move on and talk about the add instruction. In other words, we are actually going to skip some of the topics that is actually in the notes earlier. Let me switch. Oh, I think I closed that window already. Let me do this again. So what I'm saying is I am actually skipping 5.3. I'm skipping 5.7, which is the other addressing modes. I'm skipping 5.8, 5.9, and 5.10 for the time being, because those things are more of a convenience type of feature rather than a necessary feature. And I'm teaching this class as if we're dealing with a RISC processor, even though the i386 is really a CISC processor. I'm teaching this class as if we're dealing with a RISC architecture. I'm using the least number of instructions and addressing modes in order to implement whatever we need to implement. All right? So with that out of the way, we can now move on to talk about the add instruction. The add instruction is not a very exciting instruction. So we talked about binary add a long time ago. Okay, so we talked about it probably here. That may not be the only note on binary addition, because I wrote several notes on binary addition. So we'll take a look at this link here and find out whether that's the right one or not. Okay, that one talks about the addition, but not the instruction to do addition. Binary addition, half adding, maybe it's this one. Yep, that looks like it. Okay, so let's go ahead and talk about binary addition. We have done all of this already, as far as the rules of adding is concerned. So we are just basically revisiting how to add binary numbers. It's already discussed in the other module, and here's a link to the module that originally talked about binary adding. So the first thing is to revisit the rules of adding. There are only 4 rules because you can add 0 to 0, 0 to 1, 1 to 0, and 1 to 1. With each one, we want to indicate what is the result of the adding in the context of a multi-digit addition. And then we have to mention, do we have a carry to the next digit? So all of this stuff we have kind of talked about already. If you remember, your homework assignment for the subtractor is kind of like a tweak of the adder, and the only tweak is to add a NOT gate to the half adder. That's the only thing you have to do to an adder to make it turn it into a subtractor. So in this case, we talked about the function. So I'm just using a function representation and say C00 is the carry of adding 0 to 0, and R for the result, which is the result of adding 0 to 0. So now that we have these 2 functions, we are, we can define the bit operators to do that, using AND, OR, and NOT to do it. And then after that, we talked about how to use these functions to represent the result of adding. Okay. So do you still vaguely remember all this stuff? Okay. So we're going rather quickly because that's not the focus of this particular lecture. So we talked about half adding and full adding. We use pictures. We use logic sim to demonstrate all of this stuff here. And the last carry bit, or the carry all the way to the left-hand side, is significant. Okay, that one is significant for a few reasons. But for addition, the extra carry is not really that helpful. This is something that we have not talked about. So let's talk about this one. The special flag in an ALU also remembers whether the result of a computation is 0 or not. Okay, this is usually called the Z flag for 0. The equation to compute the Z flag after an add operation is basically just using a disjunction to put all of the bits of the sum together. Okay, so what do we mean by that? Let me give you, for whatever reason, the format doesn't show really well, with this text here. So I'm going to show you what it really looks like in terms of gate logic. So for that, we're going to use logic sim again. So let's go to downloads, and then we'll run logic sim. And I may not even save this one because it's actually not, may not worth saving. We'll see. All right, so we go to arithmetics, and this time, we are just going to cheat a little bit and use an adder. And for simplicity, we'll make it a very short or narrow adder. We'll just make it a 4-bit adder. Zoom in a little bit so we can get a closer look. All right, so here is a 4-bit adder. And with a 4-bit adder, we have an carry in, which is normally 0 because we are not connecting this to another adder. So we can go to wiring and specify a 0 to go to this place. So we change the value to 0. connection. So the carry in is 0. There's an input to a particular number. In this case, we can just pick we can pick a pin here and use that to connect to the input. So we can actually specify a value for the inputs. So we have input, first input, second input. Those are the two numbers that we are adding. So the first one goes here, second one goes here. It complains because the pins are not 4-bit wide. So that's why we have to change the pins so that they are 4-bit wide. So change that one to 4-bit wide. So that's good. This is the output of the adder. So it becomes the sum. So we'll just take it out first. Okay, we're going to do something with it. This is the output carry, and we'll just connect it to another pin. But this one is going to be an output pin only. In other words, we only want this pin to display what it is, the state of the carry out, but it's not going to be useful other than just indicating what is the output from the adder. This one is interesting because this one wire is actually representing 4 bits. Okay, to show you what the 0 flag is about, I have to basically open it up so it becomes 4 individual bits, because then I can show you how we are actually computing the 0 flag. Okay. But before, well, I suppose we can do that first. So we go back to wiring, and we use a splitter in this case to split one single wire in logic into 4 individual wires. So in the splitter, we have a fan out of exactly 4, and the bit width is also 4. So now we are looking at 4 individual bits, which is the output of the adder. Let's see whether this works or not. The only way we can see whether this works or not is to put a probe connecting to the output. Then we can actually see, okay, what is the output of the adder. Let's go ahead and specify some number here so we can add some number. So let's say this one is 0101, which is 5 in decimal. And let's say the second one specifies 3, which is 0011 in binary. So 0011 in binary. And the output is 1000 with no extra carry flag at the end. Is that correct? 5 plus 3 is 8, and 8 in binary is 1000. Okay, so it's all good. We don't have any carry coming out from the most significant bit because we have enough bits to represent 8 with only 4 bits. Okay. So now the question is, how do we compute the 0 flag? The 0 flag, if you go back to the notes here, and I need to find out, did I close it again? I keep losing track of this one here. It doesn't show up as a tab, so yeah, it doesn't show up as a tab. It shows up as this tab here without the Google Chrome icon. That's kind of interesting. So it is basically the disjunction of all the bits of the result, but negated. Okay. So let's go ahead and go back to LogicSim and try to represent it. So we are now looking at a disjunction gate. Okay, so let's go to the gates here, and we'll pick up an OR gate, which is disjunction. And the OR gate only needs 4 inputs because there are only 4 bits to the adder. So there are only 4 inputs here. And we'll just connect these pins just the way they connect here. All right. But the output is negated. So when you look at the OR gate here, the output is going to be negated. It has ways to negate the input, but no way to negate the output. But that's okay. We can just always use a NOT gate to negate the output. So we have a negation here. Let's zoom out a little bit so we have more room. This becomes our 0 bit. Okay, so let me just go get a pin so we can see this as an output. Make it face west. So, and this is going to be an output pin. There we go. We'll also label this particular pin because it is special to me. So this is what we call the Z flag or the 0 flag. This one is special to me because it is what we call the carry flag of, after an addition. So in this case, when I add 0101 to 0011, the Z flag is a 0, which means the result is not a 0. Is that making any sense? Okay, well, that's no big deal. I mean, the sum of 5 and 3 is non-zero. That's all it's saying, which makes sense. And there's no carry, which basically means, with 4 bits, it is enough to represent 8 as an unsigned integer. Okay, which also makes sense, right? Because with 4 bits, I can represent all the way up to 15, as a number, as a value. Okay, let's try something that is also kind of obvious. Let's try to add 0 to 0. Okay, so we'll flip some of these bits here. So we're adding 0 to 0. And you can see that in this case, the carry is still a 0, which makes perfect sense. But the Z flag this time is a 1, which indicates the sum of 0 and 0 is a 0. But do you see how the OR gate combined with a NOT gate works together to indicate whether the result is 0 or not? Okay? Because if any one bit of the sum is not a 0, the disjunction would have output a 1. And then the negation would turn that 1 into a 0, which means it is a non-zero. The only time the output can be a 0 is the input to the negation gate is a 0, but that also means all of the bits coming out of the adder must be 0. So that means the sum is 0. Here comes something that you may not expect. I can add a non-zero number to a non-zero number and end up with a 0. Let's try it. Okay. Flip this one to a 1, flip that one to a 1, and you can see that in this case, I'm adding 1, 0, 0, 0 to 1, 0, 0, 0. But the outcome is, it is a result of 0. But that's only because 1 plus 1 is a 0 with a carry. And that's why in this case, you can also see that the carry bit is a 1, because we have 1 extra carry coming out of the sum, and that needs to be represented. Are there any questions about the carry flag out of the adder as well as the Z flag coming out of the adder? Yep, go ahead.
Could you show us what happens if the result of the adder is more than 1 bit as 1? An even number, for example.
Pick a particular value.
It's 5 and 4.
5 and 4. Okay, so we will do a 5 here and a 4 here. So, and when you add 5 to 4, the result is 9. 1, 0, 0, 1 is unsigned, it is 9. And in this case, we don't have an extra carry because there are enough bits to represent 9 using 4 bits. And the result is non-zero because the output has 2 1s in it. Okay. But that's exactly how the Z flag is determined inside the processor. It is really just the negation of a OR gate combining all of the output of the result. All right. So let's move on into the notes and let's finish up this part here. This is actually, the way it's supposed to be formatted is we are looking at sum S subscript 0, S1, S2, S3, S4, and so on, and then have an over bar to cover the entire thing. An over bar means negation in electrical engineering, and a plus actually means disjunction in electrical engineering when we talk about gates. All right, so that's basically section 3 of this particular slide. And then we talk about signed numbers. Okay, we talked about 2's complement already. 2's complement is basically 1's complement plus 1. Okay, that's just the way you get to the bit pattern. But that's also how we represent negative numbers. How many people still remember the discussion of 2's complement? Okay, that's how we represent negative numbers. To be more exact, 2's complement as an operation is quote-unquote equivalent to the negation of something. We're taking the arithmetic negation of a particular value. So let's just kind of go through that topic a little bit here, just so that we have the context of this particular portion of the lecture. If you take the negation of something, let's say you take the negation of 5, the value becomes just -5. If you take the negation of a negative value, like -4, then it becomes 4. That's arithmetic negation. Are there any questions about arithmetic negation? Okay. So what I'm claiming is if you use a fixed width bit pattern to represent number, like 4 bits, 8 bits, just pick a particular width, okay? 2's complement, which I use C2 to represent using a text editor, if you take the 2's complement of a particular value, it is really the same thing as saying the negation of that value. That's what I'm claiming, okay? But does it really work out? Well, let's find out, okay? So let's say we're dealing with 4-bit numbers here, okay? So we're dealing with 4-bit numbers, because whenever you talk about 2's complement, you always have to specify how many bits are we talking about, what is the width of each number. In this case, we'll just deal with 4-bit numbers because they're a whole lot easier to write compared to 8 or 16 or even 32 bits. So we're dealing with 4-bit numbers here, and we want to say, okay, show me what is the negation of 5. Okay, that's what we want to do. Well, I cannot do a 2's complement on a base 10 number because base 10 does not lend itself to logical NOT. So the first thing we do is to convert 5 into a binary number, which is 0, 1, 0, 1 in base 2. And the base 2 part is actually implicit, so I'm not going to spend time to specify the base. 2's complement is basically 1's complement plus 1. That's one way to define 2's complement. 1's complement is really just bitwise NOT. In other words, all the zeros turn into 1s and all the 1s turn into 0s. So in this case, 0, 1, 0, 1 turns into 1, 0, 1, 0. And then we want to add 1 to it. And the result becomes 0, 1, 0, 1, 1. And I claim that this is the binary bit pattern to represent -5 when we're dealing with 4-bit numbers. That's just my claim. Okay, there's no particular way to prove that, hey, we can look at this bit pattern 1, 0, 1, 1 as if it is just -5. Okay, so I'm going to show you, why I can, I'll show you examples, not to prove, but to demonstrate, that it works. Okay. All right. So with this in mind, I can now say, what is 4 minus 5? Okay, let's figure out what is 4 minus 5. Now, without even knowing anything about binary numbers, we can kind of say 4 minus 5 is the same thing as 4 plus the negation of 5. Agreed? Sort of? Okay. So in this case, I can also, if 2's complement is truly taking the negation of a number, then I can say this is the same thing, should be the same thing, as 0, 1, 0, 0 plus the 2's complement of 0, 1, 0, 1, right? Does that make sense to you? I'm kind of combining 2 steps in one. One is from base 10 to base 2, and then the other one is to use 2's complement in place of an arithmetic negation. But is that part okay? Is everybody following why this expression can be rewritten as this expression when I claim that 2's complement is the same thing as arithmetic negation? That part is okay? All right, so let's find out whether it works or not, because maybe it works, maybe it does not. So we'll go ahead and perform 0, 1, 0, 0, which is supposed to represent 4, and 0, 1, whoops, 1, 0, 1, 1, which we have already calculated previously, because the 2's complement of 0, 1, 0, 1 is already calculated previously to be the bit pattern of 1, 0, 1, 1. So that is supposed to represent -5. So we'll go ahead and perform the addition here. 0 plus 1 is a 1 with no carry, and there's also no carry from the previous digit because this is the least significant digit. So the result of the first column is just a 1. And there's no, because we don't have any carry from either addition, so there's no carry to the next digit. 0 plus 1 is 1, 1 plus 0 is 1, and neither give me any carry, so this is going to be a 0 carry. 1 plus 0 is a 1. 1 plus 0 is a 1, neither gives me any carry, so that's a 0 here. 0 plus 1 is a 1. 1 plus 0 is a 1. And there's no carry, the overall carry from the entire addition, so this one is just going to be a 0. Okay, so we look at the result 1, 1, 1, 1, and you go like, oh, that doesn't look like negative 1 to me. There are like too many 1s in this negative 1. Well, but how do you look at 1, 1, 1, 1 and find out whether it is negative 1 or not? Exactly, we apply 2's complement to it again. Because when you take the negation of a negative value, you get the magnitude of the negative value, right? So we will do the same thing here. So we look at the 2's complement of 1, 1, 1, 1. We say by definition it is C1 or 1's complement of 1, 1, 1, 1 plus 1. And the 1's complement of 1, 1, 1, 1 is 0, 0, 0, 0. We flip all the bits, 0s into 1s and 1s into 0s, plus 1, and that turns out to be just exactly 1. So if the 2's complement of 1, 1, 1, 1 is exactly 1, and I claim that 2's complement is the same thing as taking an arithmetic negation, what do you think 1, 1, 1, 1 is representing? The value of negative 1. Exactly. So it kind of all works out. Okay. Now this is by no means a proof of 2's complement is equivalent of taking the arithmetic negation, but it is a demonstration to show you that it does work out in actual calculation. Is that part okay? All right. So if that part is okay, we're going to move on to this one here. In other words, when you just look at a bit pattern, like 1101 in this case, what is it really representing? The proper answer is, I don't know. If you just give me a bit pattern like 1101 and you ask me what is it representing, my answer, the appropriate answer is, I don't know. So in assembly language programming, we don't know what something means until we have instructions to process it. So before you have an instruction that takes this as a part of its operand and do something about it, we just look at the bit pattern 1101 and just go like, well, it's a whole bunch of bits. That's all it is. Is that okay? Because 1101, which is what, 13, can also be interpreted as the carrier's return character, which is ASCII 13. So if you present 00001101 and you send it to a teletype, printer, the good old day printers, it will just, do a carriage return, give you the next line. Well, actually, it will return the carriage to the home position. So to the printer, to the typewriter, that's what 1101 means. It's not even a numerical value. It is a command and say, oh, roll the entire carriage back to the home position. It's not a number. It does not represent a value. So until we actually use an add instruction on this one, or until we compare this value to something else, we just say, hey, it's just a bit pattern. It has no particular meaning, has no particular value that it is representing. Is that part okay? It's kind of like asking this question, okay? What is this? What is this representing? Well, I don't know. Until I draw something, there's no particular way to look at the ink inside a pen and ask what is the meaning of the ink, because I haven't done anything with it yet, right? Okay, well, that may not be a very good analogy. What about this? What does that mean? Well, it depends on the context. It also depends on who's reading it, right? To me, it can be one in Chinese. It can be a hyphen in English, right? It can be a line segment in a math class. So depending on the context, this particular stroke, horizontal stroke of a line, can have any one of those meanings. Can be the negation symbol, can be subtraction. So if you just look at this particular thing that I have just drawn on the whiteboard, it has no particular meaning, unless you have a context and say, okay, in the context of blah 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 blah, what does it mean? Well, now I can tell you what it means. Okay. So assembly language programming has a lot of stuff like this. Okay, so without the context, you just look at the bit pattern as, okay, it's a bit pattern, it's a bunch of zeros and ones, and that's all that it is. Okay, you don't try to overthink it. You don't try to overthink and say, oh, but this can be 13, can be carriage return, can also be a negative value, because it can be -3 in this case. Okay, so you don't try to interpret it in any particular way until you have an instruction to take this as a part of the value to be processed. Then you can say, oh, okay, in this context, we can look at it as blah, 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 blah. Are there any questions about this slide? Because this can be one of the more confusing part of this class. It is a very big deviation from C and C++ programming, where everything has a meaning. And the reason why in C and C++ everything has a meaning is because the programming language is called a strongly typed programming language. When you look at, okay, if x is an integer, and you say x gets 5, we know how to interpret this, because x already has a context. We are already establishing a context of how to interpret 5. But in assembly language programming, 5 is nothing more than a bit pattern of 0, 1, 0, 1. Okay. Are there any questions about all of this stuff? No questions? Okay. We will probably come back and talk about this kind of topic again, so it's not going to be the last time that we talk about this. Range of numbers. Basically, this is something that you should have picked up from the previous class already. If you have an integer that has n bits, and you want to look at it as a signed number, the range of values that you can represent is -2 to the power of n minus 1 to 2 to the power of n minus 1 as an exponent minus 1 itself. Okay, and that's why with an 8-bit number, you can represent -128 to +127. How many people got that part from the previous class? Like cisp310. Did they talk about the range of values that you can represent using an integer? Did they talk about the width of an integer in number of bits?
Yeah, but I forgot.
That's okay. All right, so the next one is to talk about the add instruction, and this is it. This is the add instruction. If you know how to use the move instruction, you already know how to use the add instruction. In other words, the add instruction is just like the move instruction, with only one exception. The source, the destination, the source specifies one of the numbers to be added. The destination is the other number to be added, but it is also stored in the destination. Okay? But that sounds kind of abstract. Let's go ahead and try this out and see if it works. So we'll go to a prompt here, and we'll just write very simple programs to illustrate a concept. So we'll go ahead and just write add.s here, and in this case, we don't need anything too special. We need to, let's say we copy like an immediate operand, let's say 4 into EAX, and we say add long 6 to EAX here, and then we'll stop in the next instruction. I don't even need to finish this entire program, because I can just put a no op here, put a breakpoint on the no op, and stop there. Okay. So if you just look at these two instructions, let me put on the line numbers so I can refer to which line we are dealing with. If you look at line 4 is an instruction that we have seen already. Okay. How do we call the first operand of line 4? It has a $sign in front of it. It's an immediate operand, which means it's literally just 4. Okay. In fact, this 4 as a constant is a part of the instruction. Okay, when you look at the binary code of this particular instruction, the bit pattern of 4 in 32-bit is a part of the instruction. Okay, because the 4 is the value that we are copying from. What is %EAX? What type of operand is it?
Register.
It's a register operand, which means we are storing the value of 4 in register EAX. Does it involve any location in memory other than the instruction itself? Nope, because it has no indirect operand. Okay, indirect operand is the one that has parentheses around a register. Okay, all right. So that's line 4. What is the effect of line 4? After line 4 executes, what gets changed?
EAX contains the value of 4.
Exactly, EAX contains the bit pattern of 4 in 32-bit. What about line 5? Okay, that's a new instruction. It's add. Okay, but since I said add is almost the same thing as move L, except we perform a calculation and store the result back into EAX. What do you think is in EAX after line 5 executes? Say again? 10. That's it. Okay, because we are adding the first and the second operand, which means we're adding the value 6 to whatever value is stored in EAX, which was 4, and then the result, the sum, is stored in the second operand, which is EAX. In other words, one thing is consistent. The second operand is still the destination. That is the one being changed. Okay, so let's go ahead and try this out in GDB and make sure that it works. It works the way we think it should. So we assemble the program, we link it, and maybe just GDB it. Put a breakpoint on line 4, run the program. Now it stops on line 4. Let's go ahead and examine EAX at this point. It is a 0. Single step, line 4 just executed. Print EAX, it is now 4. Not surprising. Single step, line 5, we're adding 6 to 4. Print EAX again, now it is 10. So the program did exactly what we thought it should. All right. Any questions about this particular sample program? No questions? All right. So now we can start to combine the add instruction with the move instruction. Okay. But before we do that, let's go ahead and finish up this particular topic. Okay. And that's basically what this is. I mean, you can add. The first operand can be anything. In other words, it can be an immediate operand, can be a register operand, can also be a memory operand. The second operand, on the other hand, which is the destination, cannot be an immediate operand. Does that make sense to you? That we cannot, have the instruction to change its own, bit patterns? Because an immediate operand is a part of the instruction itself. To store to an immediate operand means that you're going to modify the instruction itself, which means you end up with a self-modifying program. Has anyone heard of that term, a self-modifying program? No one? Okay. Well, do you think it's a good idea to have a program to self-modify itself? Generally speaking, not a very good idea. People do that for two particular reasons. Okay, if you look up the term self-modifying program, especially in the context of assembly language programming, people do it for two reasons. Reason number one is actually for efficiency. This is back in the good old days, when certain operands are not supported, and it's really cumbersome to get something done, and changing the instruction itself is one way to get something done relatively quickly. With more efficiency, but it's very, very dangerous. The second thing people do with self-modifying code is to obfuscate, okay, to make things kind of difficult to understand and difficult to track and difficult to hack. I believe Microsoft had done that, at a certain time with some of its products, so that the beginning or when the program starts execution, the way it works for the copy protection or copyright protection is not easily understood. You cannot just look at the executable and just read it and go, oh, okay, I see you are doing this and that to check the serial number and the authorization code. I'm just going to bypass that code, or I would just inject something into it to fix it, to make it work. Okay, so they make that code really hard to understand by using self-modifying code. So that way, it will be much more difficult for people to follow, what it means and how to break the protection. You can probably look up online and find some references to that. So if you look up self-modifying code, Microsoft, stepping through self-modifying code in code view. I will leave it up to you guys to look it up to find out, how people apply self-modifying code. But in general, it is not a good idea, and it's no longer possible, because if you're running your program in a protected mode operating system like Linux or Windows NT, the space or the segment that is corresponding to your instructions is read-only. So any attempt to modify your locations within that section of memory will instantly cause a segmentation fault, because you're accessing memory not the way you are allowed to. So that way, you cannot even run self-modifying code. But the bottom line is you cannot change it. Okay, you cannot change a immediate operand. So we are almost done here. After an add instruction, there are certain flags that will be changed. The first one is what we call the C flag. Is that one kind of familiar to you? The carry flag. We just talked about it, and we also, demonstrated. Okay, that's the carry flag coming out of an adder. So this one is not really a big surprise. So we'll move on to the next one. Is that one surprising? Have we seen it somewhere?
Yeah.
Yep. The sign flag is actually not too mysterious either. If I go back to the picture here and I say, okay, where's the sign flag? What is the S flag here? It is the most significant bit of the result. Okay, so where should I make a tab and connect to a pin if I want to, use a pin to represent the sign flag? Yep, go ahead.
You could probe 0 from its letters.
It's actually 3.
Oh, all right.
The most significant bit. So you almost got it. It's the most significant bit. So if I want to add a sign flag to this picture, I just take a pin, turn it into an output pin, and connect it to the most significant bit of the output of the adder. Okay, that becomes my sign bit. So the label is just a simple S for sign. Okay. Now the sign flag is kind of important in many ways, because if you want to interpret the result as a signed number, the sign flag being a 1 means it is representing a negative value. If the sign flag ends up to be a 0, it means it is representing a non-negative value. Can be 0, but it's just non-negative. Okay, so that's why the sign flag is kind of important. Okay, that's kind of cool. Let's find out, what else, what kind of other flags do we have here? Okay, this one is really odd. Okay, and no, O does not represent odd. O means overflow. Okay, but the way people look at it is like, wow, this is the one that most people have the most difficulty to wrap their mind around. Okay, it's called the overflow flag. The overflow flag, there are several ways to look at it. If you want to look at it from the quote-unquote human perspective, it basically means the result of the addition is out of range from the signed perspective. Okay, if you're adding 2 numbers and you look at those numbers as signed numbers, and the result cannot be represented given the number of bits of the adder, then the overflow flag is going to be set. If the result can be represented, then the overflow flag is going to be cleared or having a value of 0. So for this, we have to go through a few examples to best illustrate what we are talking about here. Okay. So let's try to, let's keep ourselves to only dealing with 4-bit numbers, and we'll try a few things. Okay, so we'll try How about adding -2 to -3, okay? And you already know the result is -5. So the question is -5 within the range of values that can be represented, signed, using only 4 bits? Do you guys still remember the equation? The range of values that can be represented, given the width of a certain integer, is negative and then 2 to the power of n minus 1. In this case, n is 4, n minus 1 is 3, 2 to the power of 3 is 8. So the most negative value you can represent only using 4 bits is -8. The most positive value is 2 to the power of n minus 1 in parentheses, and then the whole thing minus 1. N is 4, n minus 1 is 3, 2 to the power of 3 is 8, 8 minus 1 is 7. So the range of values you can represent using a 4-bit number signed is -8 to +7. -5 is one of those values, right? So if we perform the binary addition of -2 to -3, we should end up with a -5 value that can be properly represented. Okay, that's what we're going to try now. Okay, so -2 is the 2's complement of 2, which is the 2's complement of 0, 0, 1, 0 in binary, and that turns out to be 1, 1. Let's see. 1, 1, 0, 1, so it becomes 1, 1, 1, 0 in base 2. I'm skipping a few steps here, but you can carry out the entire calculation if you want to. -3 is the 2's complement of 3, which is the 2's complement of 0, 0, 1, 1, and that is 1, 1, 0, 1. So once we convert all of these into binary numbers, now we can say, oh, okay, so we are just adding 1, 1, 1, 0 to 1, 1, 0, 1. So if you look at the result of this, well, we'll do it step by step. 0 plus 1 is a 1. There's no carry coming from the previous digit because this is the least significant digit. And 1 plus 0 is a 1 with no carry to the next digit. We have 1 plus 0, which is a 1. 1 plus 0 is a 1, and neither contributes a carry, so the next carry is a 0. Then we have 1 and 1. 1 plus 1 is a 0 with a carry. 0 plus 0 is a 0. Then we have 1 plus 1 is a 0 with a carry. 0 plus 1 is a 1. So now we look at 1, 0, 1, 1 and say, is that a representation of -5? Well, first of all, is representing something that is negative. If I look at a 4-bit pattern as a signed number, is 1011 a negative value? It is, because the sign flag is a 1. Okay, the sign flag is just the most significant bit of the number. Okay, knowing that it is of the right sign, we can now try to look at the magnitude of this particular number. How negative is it? We can then apply 2's complement to 1011. And that becomes 1's complement of 1011 plus 1. And 1's complement, the 1's complement of 1011 is 0100 plus 1. Then it becomes 0101, which is 5. Okay? So we got the right value back. But the most important part is I added a negative number to a negative number and end up with a negative number. Thus the sign itself makes sense. And we are good, okay? Okay, but since I asked that question, it kind of implies that sometimes we can end up with a value, the result of a sum, having the wrong sign. Okay, you're adding two positive numbers and you end up with a negative value. How's that possible, right? Let's try something that looks really, really simple. Okay, 4 plus 4. We know that. Right? 4 plus 4 is just 8. Okay? So we can try to do this in binary. 0, 1, 0, 0 represents 4. So we're just adding it to itself. This one is easy. I can do it without anything else, right? Because there's only 2 1s here. And 1 plus 1 is a 0 with a carry, but since the next column are all zeros, that carry becomes the only one, as the result. But here comes the problem, right? Because now we're adding 2 positive, non-negative values. How do we know these are non-negative? The sign bit is a 0, the sign bit is a 0. But what about the result? The result has a sign bit being a 1. So if I want to look at the numbers coming in and the number going out as assigned values, the sign of the result does not make any sense. So in this case, the overflow flag will be set, because the result, which is 1, 0, 0, 0, is not representing the signed value that I want to represent, because 8, positive 8, cannot be represented as a signed value with only 4 bits. What about the other one? Okay, can we add a negative number to an negative number and end up with a non-negative value? We actually did it once already. Most of you probably did not remember, but we did it already. So we'll go ahead and specify negative 8, okay? Because negative 8 is 1, 0, 0, 0. So we want to add negative 8 to negative 8. And we should end up with negative 16. Okay? But in binary addition, using only 4 bits, that's not what we're getting back. Because now we're adding 1, 0, 0, 0 plus 1, 0, 0, 0. And the result does not require all the details. We have one overall carry, and then the rest are all zeros. But the result is only this part. The extra carry is not a part that is stored. It is just the 0, 0, 0, 0 that is considered the result of the addition. In other words, we are adding negative 8 to negative 8, and we end up with 0. Now, I know the value does not make any sense, but what about the sign? Does the sign make any sense at all? You're adding a negative number to a negative number. You end up with a non-negative number. Okay, so the sign does not make sense. So in this case, the overflow flag will also be set, okay? Because the result of the addition, the sign of the result of the addition does not make sense. Is that okay so far? All right, so if overflow is just reflecting whether the sign of the result of an addition makes sense or not from the signed number perspective, how do we make the gate logic to detect situations like this and say, oh, if we have a situation like this, or if we have a situation like this, then the overflow flag should be set. It should become a 1. How do we detect situations like that? Well, there are easy ways to do this. You look at this flag, but this bit here, and this bit here, and say this is one pattern to look for something going bad. Okay? You look at this bit here, and this bit here, and you say this is the other combination that is considered bad. In other words, what you do is you look at the 4 bits here, and I only use A here as the other bits I don't even care. Okay, the question marks mean I don't even care what those bits are. And the most significant, I only pay attention to the most significant bits of the numbers to be added, and the most significant bit of the result of the whole thing. So overflow is basically just saying if A is a 0, if B is a 0, and somehow C is not a 0, then the overflow flag should be set. Or if A is a 1, B is a 1, but somehow C is not a 1, that is also overflow. That's how we define the overflow flag using bit operations. Is that making any sense? Okay. In other words, we're converting something from the arithmetic meaning into gate logic, okay, which is what you really need to do, because everything inside the processor are done by gates of some kind, NOT gate, OR gate, AND gate. So we want to convert everything that we want to do, like detecting whether the result of an addition makes sense or not, into gate logic. So in this case, we are just taking the most significant bits of the numbers to be added and the sum in order to determine whether the overflow flag should be set or not. Any questions about this part? Questions? Well, can we do something like this using logic sim? In other words, can we look at what we have here already and say, well, let's go ahead and also specify the overflow flag. We certainly can do that. Okay, so what we'll do, or what I'll do, is to do it in a backward way. In other words, I basically would do it in a reverse way and look at, okay, we have an OR as the result, and then the OR is coming out of the AND. So that's what we'll do in Logic Sim. So we go to gates here. We specify, overall, we'll use an OR gate first, and we'll make it a narrow one because we just need 2 bits as the input. So 2 inputs to the OR gate, and then the output out of this one will connect it to a pin, and that pin will face west, and we'll call this our overflow flag with an O, and we'll make the connection here because if you look at the equation, that makes sense, because if you look at the equation, the last operation in order to get the overflow flag is a disjunction. That's why this is the gate right before the pin called O, and this one needs to be a output pin, so it's a circle. Okay, now what about the input? The input, one of the inputs is coming in from a conjunction, and the other input to the disjunction comes from another conjunction, and those conjunctions have 3 inputs each. So now we'll go ahead and create those particular gates. So this time we specify AND gates, and they have 3 inputs each. So now we can just replicate this one, Control-C, Control-V, and now we have the 2 AND gates to feed into the not OR gate. So go ahead and rearrange things a little bit here. All right. Now, how do we get those 3 inputs into each AND gate? And by the way, I don't really like it when it's too big, so I'm just going to shrink it to a smaller size. Okay. So now where are those bits coming from? Those bits, one is coming from here, one is coming from here, and the other one is coming from here, the sign bit. Okay. So the sign bit is the easy one. I'm just going to reuse the sign bit that we have here already. And we'll make it the last one. So we'll go ahead and connect this one here, and to connect it here. One has to be negated because when you look at the equation, C is the sign bit of the sum, and one is not negated, and the other one is negated. The negation can be done at the gate, so I can say the 3rd input is going to be one that is negated. This little bubble here means that input is negated before it goes into the AND gate. What about the other 2 bits? Well, they're not really as easy to get to, because I did not splice this line here. This one single line is actually representing 4 bits. Okay, it's representing 4 paths from 0101, which is the pin, into the input of the adder. So I will have to kind of splice it first, and so I can get to that bit. So to splice something, I have a splitter, and so we will hook up a. Okay, we'll do it here. Control-C, Control-V. Now we have 2 splitters, one for the first number and the other one for the second number. So we'll go ahead and make a connection from here. No. Back. Okay. Yeah, it will complain. I will fix that. All right. It complains because this is a 4-bit bus, and this is a 2-bit splitter. So we'll go ahead and change this and say the bit width is 4, and the bit width is 4.2. And once you control the width of the splitter, you can now dedicate and say, okay, which ones are the top and which ones are the bottom. I really just need bit 3 on its own. So I'll group all the other bits into the top and only bit 3 into the bottom, and do the same thing over here. I should have done this before I copied and paste, but that's okay. Okay, so now we have it all split up, and I only need to pay attention to this one here because it's the most significant bit or the sign bit. So this one is going to go here with negation, and okay. Let's see, this is the top one. Okay. Let me get rid of this one because this one's supposed to go to the top. Over here, and this one goes to the bottom. Now, when the sign bit of the output is not negated, the two most significant bits from the input should be negated. Because when you look at the equation here, the sign bit of the output is not negated, but the sign bits of the inputs are negated. So with this particular AND gate, I have to specify negation to the input to the first 2 pins. And then with the second one, I would do exactly the opposite. The sign bit of the output is negated, so that means the sign bit of the input is not going to be negated. So we'll go ahead. This does not look as good as it should, but logically it still does the same thing. So it will work. Okay. So right now it is incorrect because it's saying the sign bit is a 1 when we add. Oh, it makes sense. It makes sense. Makes perfect sense. Okay, because what we have here is we're adding a non-negative number. How do we know this number is non-negative? It has a 0 as the most significant bit. To another non-negative number, because it also has zeros as the most significant bit or the sign bit. But we end up with a value that has the sign bit turned on, which means we end up with a negative value. Non-negative plus non-negative is negative. The sign does not make sense. Guess what? The overflow flag is now a 1. Okay. Let's try the other one. Let's try to add 1000 to 1000 because that's the other one where the sign does not make any sense because we're adding a negative value to a negative value and end up with a non-negative value. Let's see if we can make that work. So we'll go back to the input, turn this one into 1000. This one into 1000, and you can see the output is 0000, and the sign, the overflow flag is a 1 because the sign of the output does not make any sense. So are there any questions about these 4 flags? Because these 4 flags are important later on in this semester, especially when we get to compare, which is basically subtraction. For addition, yeah, they're kind of important sometimes, but it's not as important as when we have to deal with subtraction. But are there any questions about the meaning of each flag or how it is actually computed using logic gates? No questions? Okay. Now both of those are important, okay? The actual meaning of the flag and also how it is derived using logic gates. They're both important in this class. Okay, so I'm going to save this file because I'm suspecting that this is going to be useful in later discussions in this class. So I'm going to save this file and we'll stash it into text processor, which is called as flags. Right. So I'm done with the lecture. I will be in the lab. If you want to do your homework and have questions to ask, I'll be there. But don't expect me to give you a direct answer, like, what should I put here in place of the question mark? I will most likely answer a question with a question. But that question will help you, get to the right answer. Yep.
Do you have office hours tomorrow?
Yes, I do. 8 to 9 o'clock every day.